Today we will learn a current carrying circular loop as a magnetic dipole. What is a dipole? Dipole means two poles. A bar magnet can be considered as dipole because it is having north pole and south pole. You have also learned electric dipole. With one positive charge and another negative, equal and opposite negative charge. This is your one dipole. It creates electric field all along space of the dipole. And this field along perpendicular bisector plane at a distance x is given by electric field is given by 1 upon 4 pi epsilon naught. This is electrostatic constant to dipole moment upon this distance cube of this distance f cube. So this is how electric field due to a dipole is given. Here the electric dipole is not the elementary source of charge. Elementary source of charge is only a single charge because a single charge also produces electric field in its vicinity, and that electric field is given by 1 upon 4 pi epsilon naught q upon, if the distance is x, q upon x square. So dipole is not the elementary source that is producing any electric field. The elementary source that produces electric field is a single charge. But in case of a magnetic dipole, here I am taking a magnetic dipole. With a north pole and a south pole, each time when you cut this dipole, here I have cut this dipole in two parts, we get is two separate north pole and south poles. You never come to a single pole, always you come to a combination of two poles, north pole and south pole. So here a single north pole cannot be realized in case of a magnet, and you will find that the electric field of a magnet, it is your electric field due to charge. Now magnetic field, okay, magnetic field due to a magnet, that is written by B, it is given by mu naught upon 4 pi to dipole moment upon x cube. This is the magnetic field given by a magnetic dipole, magnetic bar magnet at an axial point at a distance, at a equatorial bisector point at a distance x. It is bisecting, so it is your equatorial bisected point. Here when you compare electric field and magnetic field, you will find that there is some analogy. Here you have electrostatic constant and you have magnetic constant here instead. Here you have a cube of distance. Here also you have cube of distance, and this is your 2 into electric dipole moment. Here in this case you have 2 into magnetic dipole moment. But it is not the basic. Here a single pole is not the elementary source that is producing any magnetic field. Here you have a dipole which is producing the field, which is the elementary source of a magnetic field. You will come to conclusion that a single plane current carrying circular loop is also producing the same magnetic field. the same magnetic field. So let me show you how a single plane current carrying circular loop is producing the same magnetic field. Here I am showing you. I am taking one circular current carrying loop. Current is going along this way, it is coming along this way. Okay, I have drawn the circular loop. And we are interested to find magnetic field at this point P, which is at a distance x from origin O. The radius of the coil is R. Here we have to find magnetic field, and we know magnetic field due to a circular coil along its axis, and that is equal to mu naught upon 4 pi 2 pi I into square of radius upon r square plus x square whole power 3 upon 2. This is the magnetic field a current carrying circular loop produces along its axial point, and its direction can be found by right hand thumb rule. Right hand thumb rule says that when you place the curl of your fingers of right hand in the direction of current, then thumb points in a direction of magnetic field. So this is the direction of magnetic field by right hand thumb rule. Now in this equation you can notice here you have area of circular loop pi r square. So in place of this you can write area vector, and then B vector can be realized in terms of area vector. So area vector A has magnitude equal to pi r square, the area of the circle itself, and direction is given by same right hand thumb rule, same that I have taken in case of magnetic field. The same right hand thumb rule you will be realizing in case of area vector too. Same right hand thumb rule. So direction of area vector and direction of B will be same. Therefore you can write field vector in terms of area vector too. Mu naught upon 4 pi 2 I area vector upon r square plus x square whole power 3 by 2. Now we also know that there is a physical quantity magnetic moment. M, vector M, which is equal to current flowing through this circular loop multiplied by its area. And the direction of magnetic moment and area vector is same, as magnetic moment vector is obtained by right hand thumb rule. Same right hand. So how we will be realizing magnetic dipole moment's direction? So we will place the curl of our right hand along the direction of current. If current is flowing in this direction, we will place the curl of our right hand, fingers of our right hand along this very direction, and thumb will be pointing along this direction. So you find that area vector and dipole moment vector are along the same direction. But if electron is revolving around this direction, you will find that the current is in a direction opposite to electron. Then current will be flowing along this direction. Now if you place the curl of your finger along the current, then magnetic moment will come along this direction. So we are to find the direction of current only. We do not see the direction of electron, rather we will see the direction of current, because here your magnetic dipole moment is equal to current into area vector. So you have to find the direction of current only for magnetic moment's direction. Now if this distance x from the axis of circular current carrying loop is very larger than radius of the circular loop, then in equation 1 you can change this equation B. So your magnetic field B becomes equal to mu naught upon 4 pi 2 into, here it is magnetic dipole moment, 2 into m upon, and just this r should be overlooked. This r should be neglected as r is very smaller than x. So when you neglect r here and this power is cancelled, you will find that now it is divided by x cube. So see, B has come exactly same as B due to an electric dipole. Where is electric dipole? Okay. Look here, electric dipole, I am writing again this term here. This is your magnetic field, and now electric field in terms of electric dipole is equal to 1 upon 4 pi epsilon naught 2p upon x cube. So quite similar. You can see the magnetic field produced due to a circular current carrying loop carrying current I has magnetic field which is analogous to electric field due to a dipole, a negative charge and a positive charge. So you make an analogy between the two and you can say that okay, a current carrying circular loop is nothing but a magnetic dipole. So we consider a circular current carrying loop as a magnetic dipole. As its value comes equal, I should say analogous to electric field due to a electric dipole. Now this was the field along its axial point. So similarly you can make analogy and you can find magnetic field using the electric field along axial point due to an electric dipole. Electric field due to electric dipole is equal to 1 upon 4 pi epsilon naught. Here dipole moment P, vector P upon r cube. And when you make an analogy with this field, and magnetic field along a diameter due to a current carrying circular loop, then you can find magnetic field B at any point on this diametrical axis which is at a distance x from the origin. And this B will be equal to mu naught upon 4 pi magnetic dipole moment m upon r cube in analogy with electric dipole along axial point. Because there is analogy in magnetic field and electric field due to dipoles. What we learn? Note, first thing, that a plane circular current carrying coil behaves as a magnetic dipole. And it is elementary source of any magnetic field. It is elementary source. In electrostats, you will saw that a single charge is elementary source of electric field. A single charge. Elementary means basic. It is the basic source of electric field. Whereas a dipole a magnetic dipole that is a plane. This is very important. A plane current carrying circular loop is the elementary source of magnetic field. Magnetic dipole moment due to a circulating electron. We know that in an atom, an electron circulates along nucleus. In a hydrogen atom, we have single electron which revolves around the nucleus, which is having one proton. Now current due to this electron, the current I can be equal to charge per unit time, and for one circulation, if we take time as time period, capital T, and charge as E, then I is equal to E upon T. The speed of electron is V. Then we know that the speed is equal to distance travel per unit time, and therefore from here V can be equal to, if the radius of this circular path is R only, so V is equal to 2 pi R, the circumference, divided by, if it executes one circumference, then the time taken is equal to time period. So let us put the value of V, value of T, time period, from this equation in 1. Therefore, in equation 1, current I is equal to E upon 2 pi R and V goes into numerator, EV by 2 pi r. And we are interested to find magnetic moment due to this circulating electron. And so for magnetic moment we need current into area. Here we have only pi r, so we will multiply with r in numerator and denominator to get a area here. Pi r square. Now this pi r square is your area. I into area is equal to EVR upon 2. Here VR. If you multiply in numerator and denominator by m, you get mvr, angular momentum. So here is a term angular momentum and here is a term magnetic dipole moment. Here you can write magnetic dipole moment and the magnitude of it is equal to E upon 2m into angular momentum, magnitude of it. Now let us realize the direction of, and let us realize this in vector form. Magnetic dipole moment vector m is equal to E upon 2m vector L. But let me find the direction of the two. Here you have magnetic dipole moment in a direction opposite to current. Not in opposite to current. Here you have electron moving in this direction, and in opposite to that, current is flowing. So when you use right hand thumb rule and when you place the curl of your finger along the direction of current, you find that magnetic dipole moment is along inward direction. Here you have magnetic dipole moment and angular momentum. Angular momentum can be realized by the same angular momentum which is equal to r cross p. So use screw rule to find the direction of angular momentum. At this very place you find that r is along outward direction and v is along tangent direction. So if you place a screw here to find the direction of angular momentum, and when you go from vector r to vector v, direction of velocity, then the screw will go anti-clockwise direction and screw will be open and it will come out in this very direction. So you find that angular momentum and magnetic dipole moment are in opposite direction in case of circulating electron. So here we need to put a minus sign. This is your vector representation of magnetic dipole moment in terms of angular momentum. Now was there a proton? Then the current was in the direction of proton only. Current was in this direction, in that current would be in this direction, and both magnetic dipole moment and angular momentum will be in same direction in case of a proton. So do remember that these two quantities, physical quantities, are in opposite direction in case of electron, but in case of proton the two quantities are in same direction. Now magnetic dipole moment divided by angular momentum is equal to, magnitude of it is equal to E upon 2m, and this is called gyromagnetic ratio. This ratio of magnetic dipole moment to angular momentum, this is called gyromagnetic ratio, and you can find the value of gyromagnetic ratio. If you write the value of E, charge on electron 1.6 into 10 power minus 19 coulomb upon 2 into mass of the charge. Mass of electron, which is equal to 9.1 into 10 power minus 31 kg. So it will come equal to 8.8 into 10 power 10 coulomb per kg. So this is your gyromagnetic ratio. Now, can we find the magnetic dipole exact in magnitude, exact in value for an electron? So, if you use this equation for magnetic dipole moment, it is equal to minus E upon 2m angular momentum. And using Bohr's atomic law, for quantization law, Bohr's quantization, this says that angular momentum of electron in an atom is equal to nh upon 2 pi. The angular momentum of an electron in an atom is quantized as per Bohr's model. The electron is moving in an atom, and its angular momentum is conserved as per Bohr's atomic law, as per Bohr's atomic quantization law. Because, why it is conserved? Because here n is a constant, h is a Planck's constant, pi also is a constant. So angular momentum is a constant. Now, the smallest value of angular magnetic dipole moment due to revolution, ml, since it is revolving, so we should write magnetic dipole moment due to revolution, ml. This is equal to n smallest. This is equal to your E upon 2m. In place of L, you will be writing nh by 2 pi, and you will place the value of n is equal to 1. On putting n is equal to 1, you will get smallest magnetic dipole moment due to revolution, and this is equal to, let me put value of everything here, E 1.6 into 10 to power minus 19, n is equal to 1, and h is equal to 6.62 into 10 to power minus 34 upon 2 into mass of electron, that is 9.1 into 10 to power minus 31 into 2 pi, 2 into 3.14. And this value comes equal to 9.27 into 10 power minus 24. And here you have dipole moment, that is equal to I into A. So you can write unit ampere meter square. This is the smallest dipole moment due to revolution of an electron in any atom. And there is one spin magnetic dipole moment of the electron. Spin magnetic dipole moment of the electron, that is written as ms, and it has also the same value, no change, same value, 9.27 into 10 to the power minus 24 ampere meter square. And this is the cause of elementary basic magnetism in a ferromagnetic material like iron, cobalt, nickel. So always there is magnetic dipole moment in ferromagnetic materials due to this reason. This smallest value of spin dipole moment, magnetic dipole moment of an electron in an hydrogen atom is called Bohr's magneton.